Okay, so now we are going to discuss uh, the operator state correspondence. So let's just give a title. The operator state correspondence. Okay, good. So we're going to see that radial quantization is going to play a very important role. And the equivalence of physics on the plane with physics on the cylinder has very many far-reaching consequences. And our first example of one of these consequences is the operator state correspondence. So let me first of all tell you what the operator state correspondence is. Then I'm going to discuss why it's useful. And then we'll actually take a look at how the operator state correspondence is proved. So what does the operator state correspondence say? Well, here's the idea. For every local operator, for every local operator in the CFT, in the conformal field theory, there is a unique state in the Hilbert space of the CFT. Now, you might be more familiar with calling the Hilbert space the Fock space because we're talking about a quantum field theory. And that's okay if you want to say Fock space instead of Hilbert space. I don't object. But the thing that is important here is that operators and states are very different. Usually we think about them very differently. And here I'm telling you that there's some equivalence between them. So for every local operator in the conformal field theory, there's a unique state in the Hilbert space of the conformal field theory, and conversely. And what I mean by this is for every state, there is a unique operator. So this correspondence between operators and states really is a correspondence. It's one to one. For every operator, there is a state, and for every state, there is a local operator. So quite a remarkable idea. So let's now ask ourselves, why is this useful? Why is this useful? Well, you know, for most CFTs that you look at, if you ask what is the operator that corresponds to a specific state, that can be a difficult question. So let me give you an example. If you take the dilatation operator D, you should be able to find some eigenstate of the dilatation operator. So this would be some state of a definite scaling dimension delta. If you want to create an operator of a definite scaling dimension, you have to solve a complicated operator mixing problem, which will involve the full machinery of renormalization. So finding the operator's dual to a given state, well, it's hard. It's a hard problem. It can be a difficult problem. Sometimes it's easy, but it can be a difficult problem. But just knowing that there is an operator state correspondence is extremely useful. So let me give you an example of that. Um, you're used to thinking that Hilbert space is a vector space. And because it's a vector space, you know it has a basis with uh, uh, with a basis. And you can expand any state in Hilbert space in this basis. Well, now I'm telling you there's an equivalence between the set of local operators and all set of states. So the collection of local operators is a vector space. So that's a very non-trivial consequence. And we don't need to know the precise details of which operator goes to which state to understand that. Because the collection of local operators is a vector space, it has a basis. So we can say with a basis. And because of that, there's many interesting consequences that we can derive. So you know that any state can be expanded in a basis. Now we can apply this to operators. Let's say, for example, we take an operator O1, so some operator located at position x1. We've got a second operator, let's say O2, located at a position x2. And now because we've got a basis for all of the local operators, we can express this as a sum over k. K labels the different local operators. There'll be some coefficient, I'll call it C1 2k. This coefficient is allowed to depend on x1 and x2, and then we would multiply by OK. And precisely where OK is located is up to you. You can choose it. So we might choose OK to be located at x1. We might choose OK to be located at x2. Or we might choose, as I'm choosing here, that it's located at x1 plus x2 over 2. And the different choices that you make will affect the coefficients C1 to K that appear. This equation is a very important equation. It's known as the operator product expansion. So the OPE, operator product expansion. And by using the state operator correspondence, you can prove that this is uniformly convergent, this operator product expansion. So this is another example of a very important formula that traces its origins back to radial quantization. Good. Okay, so what was the idea? We've got the state operator correspondence. For every operator, there's a state. For every state, there is a local operator. So for every local operator, there's a state. For every state, there's a local operator. It might be hard to determine exactly what local operator corresponds to a given state. But the fact that there is such a consequence tells us that, for example, the space of local operators is a vector space. It has a basis. We can expand operators in that basis. And then we learn, for example, that if we take a product of two operators, we can expand that in the basis of local operators. And this gives us what's called the operator product expansion. And using these ideas, the state operator correspondence, we're able to prove that the operator product expansion is uniformly convergent in a conformal field theory. Good. So that was just telling you what it is and why it's useful. Now let's take a look at how do we prove the operator state correspondence. So let's now say how to prove the operator state correspondence. Okay. So what are we doing? We're going to study physics. So we'll study physics in d dimensions. So we're going to work on the cylinder. So we'll be on SD minus 1 times by R. So R is for the time in the radial quantization. Let's call that tau. So tau is an element of R. This, if we work in Euclidean spaces, will be a Euclidean time, but that's fine. And this is what our cylinder would look like. So let's put our cylinder over here. Make it nice and long. There's our cylinder. Good. Okay. This is the direction of increasing tau. In this direction over here, this is the SD minus 1 direction, and this would have coordinates, d minus 1 coordinates that I'll call theta. So d minus 1 angles for that cylinder. What kind of quantization will we do? We'll do equal time quantization because we're on the cylinder. We said on the cylinder, we'll always do equal time quantization. And what are our equal time slices? Well, we might imagine we've got a slice over here of the cylinder. This is tau is equal to 0. Going off in this direction of the cylinder, we've got tau is equal to plus infinity. And going in this direction of the cylinder, we'll land up at tau is equal to minus infinity. We might have another time slice over here, which corresponds to tau is equal to, I don't know, let's say minus 2. And another time slice over here, which maybe corresponds to tau is equal to 2. So all of the standard stuff that we do on the cylinder with an equal time quantization. Good. We'll continue in a moment.